this chapter of the book is on integrating multivariable functions. An actual definite integral involves chopping regions up into little pieces, taking sample points in each region, evaluating your function, multiplying by the area or volume of the region, adding all those up and taking a limiting process, so that it's the definite integral. But this first section is more of indefinite integrals. It will be, they're not really indefinite integrals. Well, some of the integration is indefinite, and part of it are single variable definite integrals in which you assume that other variables are held constant. So in that respect, they're partial integrals. And this will be crucial to how we actually calculate the definite integrals, the Riemann integrals we define in later sections. So let's just start with a partial anti-differentiation problem. So let's start with, suppose you've got a function of two variables, and you're told that the partial derivative of f with respect to x is 3x squared minus 5y squared. The question is, to what extent does that determine what the function f is? So our question is, can we say what f is, or maybe up to the addition of a constant? And so what we want to do is anti-differentiate with respect to x. So partial anti-differentiate. Nobody, that is rarely said, and you don't write the kind of partial, this round D in the notation, but the notation for it is just an integration symbol. So this is really, you should think, an indefinite integral, a partial integral, and you want to integrate with respect to x. As I said, it's just custom. Nobody writes the round D there. It wouldn't be wrong, but it's just not done. So you integrate with respect to x, assuming y is constant, because you're trying to undo partial differentiation with respect to x, where you hold y constant. So, well, you just do this. The integral of 3x squared with respect to x, x cubed. If y is constant, 5y squared is constant, so you just get that times x, so 5xy squared. And then normally you would have a plus, a constant, and a plus c, but that isn't exactly what you want here. You need something that's constant as far as x is concerned. And you were assuming y is a constant. In fact, you could have any function of y here. It doesn't even have to depend on y. It could be an actual constant, but it can't depend on x. So we usually write something like a of y to indicate it's not a function of x. So there are two ways to look at why there's this function a of y there. You can either think, well, y is a constant as far as x is concerned. So when we have plus a constant here, it can have y's in it, because y is a constant. Or you could think, we're undoing partial differentiation, and we want to put the most general thing here that you could possibly have for f, whose partial derivative would be this, whose partial derivative would be 3x squared minus 5y squared. Well, if you add any arbitrary function of y here, the partial derivative with respect to x will make that part 0, and of course, any function of y here won't matter. Since the partial derivative of this with respect to x is this, you can put any function of y there at all, and the partial derivative with respect to x will be what you want. So this is what we write for the general answer, that to what extent does this equation determine f? It determines it up to adding this arbitrary function that's allowed to depend on y, but not on x. So this is what we get. All right, what about a definite partial integral? So this is an indefinite integral, anti-differentiating. What if we take the same example, but now put some limits of integration in there? So the limits I want are the integral from 1 to 2, 3x squared minus 5y squared dx. Well, now it's a definite integral, and the definition is, you take the limit of Riemann sums. But, and now you need to think, we're integrating with respect to x. This is what x does. X goes from 1 to 2. You need to be careful to remind yourself that it's what x does, not what y does. And you have these Riemann sums for different values of y. But, of course, how do we evaluate such things? You produce an antiderivative. Well, we just did that in the last example. This is the same integrand that we had before. And if you use the fundamental theorem of calculus, it says, oh, you produce an antiderivative, you evaluate at 2, and you subtract the value at 1, then what do you get? You get the antiderivative that we just produced a minute ago, with this arbitrary function of y here, but you evaluate as x goes from 1 to 2. Now, normally on these evaluation bars, you don't write x equals, but when doing these iterated integrals, when using multivariable functions and there are different variable names floating around, it's, you don't have to do it as long as you keep it straight, but I'll try to always do it, to write x, explicitly write x equals 1 and x equals 2, just to make it clear what's being evaluated. So what does this mean? You plug in x equals 2 and you subtract what you get when x is 1. So when x is 2, you get 8 minus 10y squared plus a of y. And you subtract what you get when x is 1. And when x is 1, we get 1 minus 5y squared plus a of y. So what do you get? 8 minus 1, you get 7. And then minus 10y squared minus minus, so plus 5y squared, so minus 5y squared. And then notice that the a of y's cancel. You've got a of y and then minus a of y. So it doesn't matter what a of y is, it gets wiped out. Well, that was the same thing that happened when you had the plus c in single variable calculus. Yeah, when you're writing an indefinite integral, so an antiderivative, you have this plus c there, and you can put it in when you do the definite integral. If you had a plus c here, you get a c minus c, so it would cancel out, which is why when we're doing definite integrals, we don't usually write the plus c. You don't need the most general antiderivative, you just need one. So that happens here in these partial integrals where you're taking a definite integral but with just respect to one of the variables. You don't need to bother writing this plus an arbitrary constant, but so an arbitrary function of what the variable you're assuming is constant, or if you had more variables, all the variables you're assuming are constant, because that constant function, that function of the other variables, will get subtracted away and cancel out and disappear. Okay, well, let's look at another modification of the same thing. So suppose we take, once again, getting kind of boring here, but let's take 3x squared minus 5y squared again, dx. All right, so we're integrating with respect to x. The y is a constant. Well, your limits of integration, I had 1 and 2 in the last example, but they could be any constants, but they could be constants. They just need to be constants as far as x is concerned to have a reasonable definite integral. But that means they could be functions of y. So for instance, we could have the sine of y here, and y raised to the 7th power. Right? Then how would you evaluate this definite integral? The same way we did before. Use the fundamental theorem. You just take an antiderivative of this with respect to x. So you get our x cubed minus 5xy squared. But the a of y, we know it's going to cancel out, so we don't bother writing it. And you just evaluate as x goes from the sine of y to y to the 7th power. So what does this mean? It means now you plug in x is y to the 7th, and you subtract what you get when you plug in x is the sine of y. So we get y to the 7th cubed, so that's y to the 21, minus 5 times y to the 7th times y squared, that's y to the 9th. And you subtract what you get when x is the sine of y. And so you subtract what you get when x is the sine of y. We get sine cubed y minus 5, and then sine of y squared. I'll move the y squared to the left just so I don't have to write some extra parentheses, y squared, sine of y. Okay, this won't simplify nicely, but this is what you get. It's a function of y. Well, that's not surprising. We had, in fact, it kind of has to be. We had limits of integration that contained y's in it, and y was a constant as far as this whole integral was concerned. But this is what you get, a function of y. It is what it is. But once you start doing that, well, here's a function of y. We could integrate that with respect to y. So this is where the iteration of the integrals comes in. Let's look at a different example, and finally I'll change my integrand. Just to make it a little different. Let's look at what would you mean by the integral from 0 to 2, the integral from y to y squared of 5x plus 2y dx and then dy. All right. What does this mean? Well, I put in the square brackets, so hopefully it's clear. You do this inside definite integral with respect to x. It's a partial integral with respect to x. You integrate with respect to x, you'll put in these limits of integration, you get a function of y. And then you'll have that function of y, and you're supposed to integrate it with respect to y from 0 to 2. So this is what's called an iterated integral, because we've iterated integration. And you do these from the inside out. Of course, the square brackets make it clear that that's what you do. I mean, this thing is in brackets, so you're supposed to do this separately and then do this. The bad news or good news, if you don't like writing a lot of notation, is nobody writes the brackets. It's what it means, but you're just supposed to know that that's what it means. Nobody writes the brackets. Everybody just writes this. And you're supposed to know that it means you do this inside integral first and you work your way out. If there were, you could have 3 integrals, so you can have 15 integrals in a row, and you work your way from the inside out. And you're just supposed to know this integral sign goes with that differential, this integral sign goes with that differential. Okay, well, knowing that, what do you do to calculate this? You calculate the inside one first. So you take the integral, so the integral from 0 to 2 will sit there. In fact, I'll put the square brackets back in. You integrate this with respect to x, so you get 5x squared, assuming y is constant, you get 5x squared over 2 plus 2xy. And this is evaluated as x goes from y to y squared. And then you integrate that with respect to y when you're finished. So what do you get? You get the integral from 0 to 2. All right, we're putting in x is y squared. So we get y squared squared. That's y to the 4th over 2 plus 2 times y cubed, y squared times y, plus 2y cubed, minus what you get when you plug in x is y, so a minus 5y squared over 2, and minus, still minus this, minus 2y squared. All right, and then you integrate this. This is now a one-variable calculus problem. You integrate this with respect to y. If you want, you can combine these last 2 terms. Now this is a minus 5 halves. That's a minus 4 halves, so it's minus 9 halves y squared. So you could simplify that before you do the integral. Not like that's a big time saver, but you can do it. And then you integrate with respect to y. So you will use the power rule. You add 1 to that exponent, divide by the new exponent. So we get y to the 5th over 2 plus, you integrate this, you get a y to the 4th over 4 times 2. So that's plus a y to the 4th over 2. Minus, you integrate this, you get y cubed divided by 3, but that'll give us a minus 3y cubed over 2. And you evaluate as y goes from 0 to 2. I don't bother writing y equals 0 and y equals 2 because y is the only variable left, but it wouldn't be wrong to write that. You plug in 2, you get 32 divided by 2, 16. 16 divided by 2, 8. Then 2 cubed, 8 divided by 2, 4 minus 12. So we get 24 minus 12. Minus what you get at 0, but at 0 all the terms are 0. So you get 12. All right, well that's an iterated integral. I just want to do one more iterated integral. And that will be it for this part of this section. So, as a last example, let's look at the iterated integral, the integral from 1 to 3, the integral from 0 to the sine of x of 1 plus 2y over the sine of x. And if I didn't tell you which order to do the integrals in, you should know from the limits of integration. These limits of integration have x's in them. So in that integral, x needs to be a constant, which should mean you're integrating with respect to y. And then we'll put a dx out here. So this integral sign goes with that. This one goes with that. You do the inside one first, and then you move out. So what do you get? Well, you get the integral from 1 to 3. You're integrating with respect to y. So this x is constant, sine of x is a constant. You just get y plus y squared over the sine of x, evaluated as y goes from 0 to the sine of x. And you'll integrate with respect to x after that. So you get the integral from 1 to 3. You plug in y as sine of x. You get sine of x plus sine squared of x, but divided by sine of x. So you get sine of x divided by sine of x, you'll get a 1. Sine squared x divided by sine of x, you'll get a sine of x. This minus what you get when y is 0, which is just 0. So this is all you're left with. The integral of 1 plus sine of x with respect to x, well, that's easy to integrate. You get x minus cosine of x, and you evaluate from 1 to 3. So you put in x is 3, and you subtract what you get when x is 1. It's not like this is going to simplify greatly. You get a 3 minus 1, so that's a 2. And then you just have minus the cosine of 3 minus minus, so plus the cosine of 1. What's the cosine of 3 and the cosine of 1? Nothing nice, but that's what you get. Anyway, this is these are partial antiderivatives in iterated integrals. They're not particularly difficult. You just do a series of one variable integrals, working your way from the outside in. In the more depth part of this section, we'll look at triple iterated integrals where you'll have an x, y, and a z. But you do the same thing. You just work your way outward to doing single variable integrals, pretending variables that are farther out in the integral are constants. The difficulty comes in when we actually want to do Riemann sums and the definite integrals of chopping up regions in R2 and R3, and what that has to do with calculating iterated integrals, but we'll get to that in the next section.